Good afternoon. For various reasons, lithium-ion batteries now get widely accepted as main ship power sources for commercial aviation. So today we'll review the concerns with lithium-ion, the expectations, and try to describe a safety methodology to build confidence and demonstrate compliance. Combustion and its end effects are the primary concern with lithium-ion. Here we summarize the three elements necessary for any fire to be initiated and sustained. Within the context of a lithium-ion battery, the electrolyte provides the fuel, the atmosphere and decomposition products equate to the oxygen, and thermal runaway supplies the heat. Unfortunately, the aviation industry's concerns are justifiably based upon ongoing consumer product issues. Industry is challenged to find the proverbial silver bullet that does not reduce the significant benefit that lithium-ion offers. Compared to its predecessors, lithium-ion provides increased energy density, which reduces both battery size and weight. However, system considerations mandate a review of the viability of individual proposed solutions. There is no one-size-fits-all. So as we look at the problem, thermal runaway involves a degradation of the lithium-ion cell, and it progresses as the cell is unable to shed, increasing heat. A hotspot or internal short circuit feeds decomposition of the cell components. Of course, this varies as a function of the specific cell electrochemistry and component selection within the cell, but the progression is similar for all cells. Degradation can result from a cell assembly defect, or can be instigated from operational abuse. So the cell temperature continues to rise, leading to cell venting of the emissions and at times particulate debris, with cell temperatures rapidly approaching to 600 degrees C, which can then auto-ignite the electrolyte solvents. So what do we do? The RTCA formed a special committee some time ago to review lithium-ion issues and the inadequacy of the then-current DO-311 standards. Two far more rigorous expectations for testing were implemented at the battery level. One was overcharge, fundamentally an expansion of the prior single-cell test, or overheating, a new test introduced to force the cell decomposition and to drive the cell into an ultimate failure. A valid test under these mandates require that thermal runaway must be observed. Valid solutions to resolve the safety expectations have to thus consider reduction of cell reactivity, that is, reduce the thermal response in anticipation of a potential failure, and two, to manage cell emissions following a thermal runaway event. So now we'll examine the key elements of a safe battery design. With the battery management system, so it's understood that a BMS is required to mitigate against abusive cell conditions, protect against external short circuit that could lead to cell venting, overcharge or overvoltage, which can plate lithium from the matrix cathode onto the anode, overcurrents or overrate, which degrades the separated material and results in plating of lithium, undervoltage or over-discharge. We actually pull oxide coppers from the substrates of the anode onto the cathode material. Low temperature, recharging when cold. Lithium plating can then result on the anode. And of course, high temperature degrades the cell materials. When we look at cell selection, decomposition of the anode's passivation solid electrolyte interface can lead to thermal runaway. Cathode decomposition, as we discussed earlier, can itself generate oxygen to lead and feed combustion. So ideally, we'd need to seek to choose a less reactive electrochemistry to minimize the failure event. Here we look at the relative energy released from the cathode following a differential scanning telemetry test. And this is simply a test where we heat the materials and look at the response temperature. The most reactive materials, as shown in this graph, consist of the cobalt-based cathodes, the higher energy variations. Iron phosphate, shown near the bottom, is the least reactive and is often referred to as a safe electrochemistry, although it doesn't serve all purposes well. So lithium-ion is comprised of a broad family of chemistry variants, mostly differentiated by the cathode composition. LFP, or iron phosphate, is typically a heavy solution, but supports high-rate discharges, relatively low energy. NCA and NCM variants, cobalt-based, typically offer the highest energy densities. When we look at the cell solution, we want to think small. If you look at a failure event, the simplest way to limit failure propagation is to look at an accumulation of smaller capacity units. And testing is essential. Evaluating cell performance to remove outliers improves both performance and safety. And that's especially true given the lean towards commercial cells. Screening is absolutely essential. We'll look at components within the cell, the electrolyte. Electrolyte modifications can further reduce the cell reactivity, but at what cost? Here we look again at the differential scanning telemetry results, and we can see that a notable improvement in cathode reactivity can be achieved for NCM and even the iron phosphate. Eagle Pitcher has been working to optimize reduced flammability electrolyte that does not degrade performance at temperature. When tested within small cylindrical 18650 format cells, we see the first figure to the left reveals favorable performance of the RF electrolyte versus a baseline for low rate discharge capacity across temperatures down to minus 40 degrees C. When we look at the second figure to the right, we show a comparison between the baseline and the RF formulation up to a sustained 2C discharge rate. Continuing to look at the electrolyte, we modified a DO311A overheat test that we mentioned earlier to now include a spark emitter. And we compared the baseline response to that of Eagle Pitcher's reduced flammability electrolyte. So here on the left, we can see that the RF electrolyte supports a more gradual degradation of the NCM cell with no flame resulting. Whereas when we look to the right, we see that the baseline electrolyte is pushed to a significantly higher vent temperature with a resulting flame. Another component of a design consideration would include cell insulation or isolation. If the element itself is of concern relative to propagation, how do we isolate it from the others within the battery assembly? So efforts to minimize cell-to-cell propagation focus on limiting the transfer of heat from a failed cell to those adjacent. That may involve physical spacing, insulative coatings, or physical barrier materials that can help limit and contain a potential thermal event. So individually, none of those stand as sufficient. And so we have to look at a layered system that utilizes many elements in order to combat the end effects that lithium-ion would offer. So with the forced cell failures conditions of DO311A, there's a demonstrated need for secondary or layered protections. A competent BMS, battery management system, is paramount to negate abusive operational conditions and is assumed part of any lithium-ion battery assembly. As we discussed earlier, recall the design objective for safe lithium-ion batteries: 1, to reduce cell reactivity, and 2, to manage cell emissions. So these complementary design efforts should include: 1, cell chemistry and format selection with distributed cell arrays with small capacity cells, cell testing necessary to ID outliers. 2, a suitable RF electrolyte optimized to reduce cell reactivity and yet preserve the functional needs for the particular application. The 3, a means to isolate or insulate the cells themselves and subsystems within the battery assembly with coatings or barriers to reduce the likelihood of failure propagation. In conclusion, as with all system development efforts, trade-offs must be managed. Cell electrochemistry must balance the need for energy, capacity or runtime, versus power, which is rate or peak amperage delivery. Cell insulation can hamper the real need to drive heat into the cells for cold temperature operation or to shed heat when under high loads. Battery case materials must balance thermal capability, strength, and conductivity needed for EMC shielding of the critical BMS assembly. Notably, the incorporation of layered mitigations will degrade overall battery volume and weight. However, when we look at the net result, lithium-ion still offers a weight and volume advantage, even with the overhead of the required electronics and mitigations. And lastly, aggressive BMS controls may protect the cells, but they could negate a functional need for the battery. This is where system safety assessments, hazard analyses, and the like can avoid conflicting BMS control settings.